Hello everyone, welcome you all for this lecture. So in this lecture I'm going to explain what is the flip-flops and how to design a different types of flip-flops. Okay. So before going to the topic of flip-flops, we'll discuss the differentiation between latches and flip-flops. Okay. So in my last lecture, previous lecture, I have explained what is a latch and how to design a latch. So latch is a transparent because the input is directly connected to the output when enable is high. Okay, but flip-flop is in a pair of latches. It is sensitive to pulse transition. Okay, and the important thing is in the flip-flop is the signal only propagates through on the rising or falling edge. That is, in flip-flop we are going to use the edge trigger. Edge triggering we are going to use, but in latches we are going to use level triggering. Okay, and the second differentiation is in latches, less number of gates only we are going to use, so it occupies less area. But here, more number of gates will be used in the flip-flops, so here it occupies more number of areas. Okay, so here the power consumption is very less because less number of gates used. Here the power consumption is more because more number of gates is used, and the latches the operation speed is high, but in a flip-flop the operating speed is low because of more number of gates. And here it requires more tool manipulation and more hand calculation to verify that they meet timing. And here we are going to use static timing analysis tools. So the important thing is latches operates with the levels in triggering and flip-flops operates with the edge. That is a very important thing in this. Okay, so these are all the few differentiation between latches and flip-flops. Next, we'll move to the flip-flops. So flip-flop introduction. First, how to design a flip-flops. See, we can implement flip-flops in two methods. The first one is the cascade of two latches. So we have designed NAND latches and OR latches, right? So this is a cross-coupled SR-based NAND latch. This is what latch. Okay, when we are connecting this kind of two latches together, that is called one flip flop. This is one way to design, and the another way is we can directly use the edge sensitive. So these are the two methods to design a flip flops. Okay, let's see. And the types of flip-flops, there are four different types of flip-flops is there. The first one is SR. So S for set and R for reset. And D flip-flop, this is the delay or data flip-flop. And JK, this is one scientist named Jack Kilby who invented the JK flip-flop. And T flip-flop, this is for toggle, T for toggle. These are the four important flip-flops which we are going to discuss in this lecture. Set reset flip-flop, delay or data flip-flop, jack can be that is a JK flip-flop, and toggle flip-flop. We'll see one by one. So the first one is SR flip-flop. It operates so only the positive clock transition or negative clock transition. It depends upon our design one. Okay, fine. Because in clock signal it contains both positive and negative. Okay, this is positive and this is negative. So the flip-flop is going to operate either one of this level, that is positive or negative level, otherwise positive edge or negative edge. Okay, fine. So the circuit diagram is shown in figure. So see, as the previous slide I told you know, we are going to concatenate two latches together. So this is latch number one, and this is another one latch. Okay, fine. So see here four NAND gates are involved, and two inputs S and R is given, and one clock signal is given. So if clock is present, definitely that device is in a flip flop. If there is no clock, then that is belongs to latches. Okay, and two outputs Q and Q bar is there. Okay, fine. And this is the block diagram of SR flip-flop. See, S and R is the input, Q and Q bar is the output, and one clock signal. Okay, so draw the square box and mark all these things. This is what the block diagram of SR flip-flop. Okay, right? So now let me explain the working principle of SR flip-flop. That is, two input is there, so two input means four possible combinations will come. That is, the first combination is S, R and Q, Q bar. So first I am going to apply it is 0 0 and here the clock is high always. Okay, fine. S and R is 0 0. So the first condition in flip flop is first erase whatever stored in the flip flop and assign some new values in the place of Q and Q bar. So I'm going to assign it is 0 and 1 or 1 and 0. So it's your choice. Okay, so I'm going to take it as 0 and 1. So my first condition is 0 0 and the clock is 1. So here 0 is there, here 1 and here also 1. So 0 1 in NAND gate it is 1 and the bottom here 0 1 NAND gate it is also 1. Okay, let me take this third NAND gate. So for the third NAND gate, the inputs are now this is 1 and already here 1 is there, so this one will come here. So now 1 1 it should be 0. Now this 0 will goes to the input of the fourth NAND gate. So here 1 0 is there, so the value is 1. See, 0 and 1 is coming and previously we have taken the value as 0 and 1. So there is no change. So here the same Q and Q bar will come and this condition is called as no change condition. Okay, right. This is the first combinations of input and second I'm going to consider the clock is 1 and my S and R values are 0 1. Okay, so this is 0 and this is 1 and again here I'm going to take this is 0 1 1. So clock is 1, so 0 1, so here output 1 will come and here bottom 1 1 is there, so here output 0 will come. So here third AND gate one of the input is 1 and here already 1 is there, so this one will come here, so 1 1 again here it is 0 and now this 0 will comes as an input of this fourth AND gate. So this is 0 and here 0 0 0, now it is 1. So now see here Q is 0 and Q bar is 1. So Q is 0, Q bar is 1. So this condition is called as reset condition. Okay, so why it has called as reset condition means S is equal to 0 and reset is equal to 1. Okay, so the condition is depends upon this S value. So here S is 0, Q is 0. So set is not available, so the condition is automatically it is the reset condition. Okay, now and the third combination is clock is 1 and S and R is I'm going to apply it is 1 0. See 1 0 again here I'm going to take my inputs are 0 and 1 only. So this is 1 and the clock is 1, clock is 1 and R is 0. So here 1 1 is there, 1 1 means this is 0, here 1 0 is there, so this is 1. So here 1 is there, so this one will comes here. So this is 0, this is 1. So 0 1, now Q is 1. So this one will comes to the input of this fourth triangle. So here this is 1 and here already 1 is there, now 1 1, here it is 0. See, now the outputs are getting 1 0. So S is 1, Q is 1, so this condition is called as set condition. Okay, and the last one is, so clock is 1 and these two are 1 1. So S is 1 and R is 1. Again here I am going to assign. See the previous output is what? 1 0 1. So I am going to consider this 1 and this 0. So 1 1. So clock is 1 and here also clock is 1. So 1 1. So this output is 0 and here 1 1. This output is 0. Okay, now third gate input is one of the input is 0 and another one input is here also it's coming as a 0. So 0 0 here, now the output is 1. Now this output 1 will goes here as a fourth and gate input. So 1 already here 0 is there, here 1 is there, so 1 0, the output is 1. See, now both outputs are 1 1. So both outputs are 1 1 means Q and Q bar is not satisfied, which means if Q is equal to 1, Q bar should be 0. If Q is equal to 0, Q bar should be 1. But for 1 1 conditions, now we are getting both outputs are 1 1. So this is not in a flip-flop condition, so this condition is not allowable here. Okay, so this is a forbidden state. So the condition is forbidden condition. So this is what the SR flip-flop or working condition. Okay, so for 0 0 condition, it has no change. 0 1, S value will goes to Q, that is reset condition, and 1 0, S value will goes to Q, it is 1, that's set condition. For 1 1, this condition is not allowable in SR flip-flop, so that's why it is called as forbidden state. Okay, right. So have a look at this. This is the timing diagram and truth table of SR flip-flop. So just now I have explained the truth table. So 0 0 it is no change condition, and 0 1 it is reset condition, and 1 0 it is set condition, and 1 1 it is forbidden condition. Okay. So have a look at this. This is timing diagram. So first S value was here 1. Okay, and R value is up to this point R value is 0. Okay, so R value is 0 and S value is 1 here, and S value is 0 here, and S value is 1 here. So while checking this condition, okay, 1 and this place is 0, 1 0, according to 1 0 Q is 1. See, 1 0, this Q value is here 1. Then this is 0, this is 0, so no change. So no change means previous output will be remains same, so again it is 1. So now again S value is changed into 1, so 1 till R value is equal to 0, so 1 0 again it is 1 1. Okay, so now here S value is changed into 0, R value is changed into 1. Okay, so 0 1, what is Q value? It is 0. See, 0 1 Q value is 0. Okay, and again this is 0, here R value is 0, so 0 0 again no change, so previous output will remain same. Okay, then here S value is 1 and R value is 0, so Q value is 1 1 0, the value is 1, and this condition is, this is 1 and R is also 1, so this condition is forbidden condition, so here we can't be able to predict the output is 0 or 1. Okay, then again here this is 0, this is 0, so and before that here one condition is there, 1 and 0, so 1 and 0 again this value is 1, and now here 0 0, so there is no change, this value is 1. Okay, so in this manner only we are going to draw the timing diagram of a flip-flop. Okay, so for drawing this in a timing diagram, this truth table is very important. Okay, if you know the working condition of SR, then you can easily draw this pattern. Okay, fine. Next, characteristics table. So how to create this characteristics table? So this is an SR flip-flop. So we know that S and R two inputs. Okay, and actually, sorry, and here this 2 will come, and present inputs here or and S will come. Okay. Fine. Let me explain. Okay. So see here, here S and R is there. So S and R, we know that it is a two input, so four possible combinations will come. So two times I have taken a 0 0 and two times 0 1 and two times 1 0 and two times 1 1. Why I have taken a two times means because Q is the present state. Okay, Q is the present state. It's a single variable, so one time I'm going to consider the value is 0, another time the value is 1. So that's why, see, the first 0 0 condition I have taken a Q is 0, the second 0 0 condition I have taken Q value is 1. The same manner for all the three remaining conditions also I have taken a 0 1 0 1 0. Now this is next state. As per the SR flip-flop truth table, I'm going to fill this next state condition. See, when both the inputs are 0 0, as per the SR flip-flop truth table, if it is 0 0, then there is no change in the present state. See, present state is 0, the same 0 only will come here. Then again 0 0, so the present state 1 will come 0 because the condition is no change condition. Then 0 1, whatever in S that will goes to the outputs, don't bother about the present state. Okay, so for these two conditions, the values are 0, 0, 1 because here alternate values 0, 1, 0, 1 is there. Then the third one 1, 0, 1, 0. So for this condition also the S value will goes to the output. So S value is 1, 1. So here 1, 1 is coming. And 1, 1 condition, we know that it is in a forbidden condition. So the outputs are don't care, don't care. So this is what a characteristics table of SR flip-flop. Now we are going to find the characteristic equation for SR flip-flop, that is for this Q of t we are going to find the expression using a K-map simplification. So we see here S and R two inputs and one present state, totally three variables there. So we are going to take a three variable K-map to find the expression for this next step. So here how many places Q value is equal to 1 1 2 3 4 5. These two are don't care. Have a look at this. 5 values are filled and here one, this is quad and one pair is coming. So this is what our characteristic equation for SR flip-flop. S plus R over Q of t. Okay, fine. And the next thing is excitation table. So how to design this excitation table from the characteristics table. So this is the characteristics table. Just now I have explained. So have a look at this. While deriving this excitation table, Qn and Qn plus 1 is going to act as an input, S and R is going to act as an output, which means, so Qn and Qn plus 1 is input means two variables, so four possible combinations 0, 0, 0, 1, 1, 0, 1, 1. We can directly write these four combinations here. So for these combinations, so what is S and R we are going to find from this excitation table. Okay, so have a look at this. This is 0, 0 and here also 0, 0, two conditions is there. Only look at this Q and Q plus 1. Okay, in two places 0, 0, 0, 0 is there. Okay, so for these two conditions, what is S and R value? S value, R values for one condition is 0, 0 and the another condition is it is 0, 1. That is, S value is same value but R value is 0 and 1. So now I am going to do the merging operation here. So this 0, 0 is merged as 0, 1 in. But here 0, 1 is there. So this 0, 1 is I'm going to use as a don't care because one time I'm going to use 0, another time I'm going to use 1. So see here it is 0, don't care. And the next condition is 0, 1. Have a look at the 0, 1, where it is 0, 1. Here one condition 0, 1 is there. I think only one condition 0, 1 is there, right? So for this condition, the S and R values are 1 and 0. See, 1 and 0. Then 1, 0, how many conditions are there? 1, 0. Here one condition is there. I think only one condition. For this condition, the value is 0, 1. So see, it is 0, 1. And for 1, 1 condition, here 1, 1, 1 is there and here 1, 1, 1 is there. So look at the corresponding values. Here 0, 0 and here 1, 0, which means this 0, 1 is represented as don't care and this 0, 0 is represented as 0. So the don't care 0 is the answer. So see, don't care 0 is the answer for this SR flip-flop. So this is what the excitation table of SR flip-flop. So I hope you guys understand the working principles of SR flip-flop and the truth table construction, characteristics table, characteristic equation, and excitation table. Okay, fine. We'll move to the next thing, JK flip-flop. So JK flip-flop is a modified version of SR flip-flop. The first three conditions are similar to the SR flip-flop, that is 0, 0, 0, 1, 1, 0. These three conditions are similar with the SR, but the last 1, 1 condition only different in JK. Okay, and this also works depends upon the positive block or negative block transition. Okay, see the block diagram of JK flip-flop. J and K are two inputs, block is another one input, Q and Q bar. So this is what the block diagram of JK flip-flop. And have a look at the circuit diagram. It is similar to SR flip-flop only, but one small change is, see this feedback Q bar is connected with the J, this first NAND gate, one of the input, and here it is connected to the this second NAND gate, one of the inputs. Okay, so let me explain with that again the same concept JK. So first I am going to consider this is 0, 0 and first erase everything and store some new values here 0, 1. Okay, so 0, 1 means here clock is 1, so these two places 1 1, and here the feedback is it is 1 is there, so that 1 will comes here, and here 0, that 0 will comes here. Now have a look at this. Gate number 1, 0 1 1, in AND gate 0 1 1, the value is 1, and similarly gate number 2, 0 0 1, it is 1. Okay, so this is 1, and now here 1 is there, that 1 will comes here, so 1 1, here it is 0, and now this 0 will comes here, so 0, and this is 1, so 0 1, the result is 1. So have a look at this. 0 1 now, previously we have taken here 0 and here taken 0 1 now, so both are same. So just now I told you know the 0 0 1 0 1 1 0, these three conditions are similar with the SR flip flop. So for this JK flip flop also 0 0, this is no change condition. Okay, let me take 0 1 condition. So this is 0 and here 1, and the clocks are 1 1, and the feedback again it is 0 1, so here 1 will come, and here 0 will come. So 0 1 1, it is 1 only, 1 1 0, it is 1 only. Okay, so again it is 0 1 only will come. Okay, so 0 1, that is J is 0 and Q is 0, the same condition, reset condition here. Okay, so now I am directly moving to the 1 1 condition. So for 1 1 condition, so J equal to 1, K equal to 1, and my previous outputs are 0 1. Okay, so now clock is 1, here clock is 1, and the feedback is here 1, and this is 0. Sorry, here it is 0. Fine. So 1 1 1. All three are 1 in the first NAND gate input, so it should be 0. Okay, and here 1 1 0, so this should be 1 now. Okay, now feedback. So here 1 is there, that 1 will comes here. So now 0 1, the output is 1 here, and that 1 will comes here. So already here 1 is there, so 1 1, now it is 0. So see here, now here output is 1 and here output is 0. So which means the previous output is here 0 and here 1. See, this 0 was now inverted into 1 and your 1 is inverted into 0. So this is what the condition is called as toggle condition. So toggle means inversion. So 1 1 here toggle, and here 1 0 it is set. So see, so as I already told you know, first three conditions are similar with SR flip flop, so no change reset set. But for 1 1 conditions it is toggle. So toggle means it is going to toggle the previously stored value. So previously stored values are 0 1. Now for 1 1 condition it is changed into 1 0. So the condition is satisfied. So I hope you guys understand. So have a look at this. First one is no change. Then here for 1 0, that is J is 1 means here Q is 1, J is 0 means Q is 0, and for 1 1 conditions it is a toggle. Okay, the previous Q output will be toggle, that's why here Q bar is written. Okay, fine. So this is the truth table of JK flip flop. Then the timing diagram, just now I have explained for SR flip flop. Okay, once again see J is equal to 0. So for drawing this timing diagram, first we supposed to draw this vertical lines. Vertical lines are very important because this only going to define the timing interval between the datas. Okay, so first draw this vertical lines. Okay, then first the clock signal is there. So the clock signal, how I'm going to draw? See, this is, looks like square pulse. So like this, I'm going to draw the clock pulse. So this is clock, then J value. So first condition is what? 0. So 0, I'm going to draw 0. This is 0 and K is also 0. So 0 0, what is Q? It is no change. So no change means first I'm going to consider it as 0 only. So Q is 0. Okay, second condition. J is, sorry, up to this, because this entire time period is one clock signal. One positive and one negative. Okay, so now for the second clock pulse, I'm going to change my this is a 0 and k value should be 1. So this is 1. So for this condition also q value is equal to 0. Okay, so further I'm going to change this is 1 0 1 and this is 0. So for this condition the q value will be changed into 1. So see the same concept only here they have used, that is 0 k is 0 and q is 0. Okay, and next one here j is 1 k is 0 so q is 1. Then here j is 1, k is 1. So which means it is going to toggle the previous output. What is previous output? Previous output is 1. So now the output is 0. And here 1, 1. So the previous output is 0. So for 1 condition it is going to toggle this 0. So now it is 1. 0, 0, no change. So the previous output is 1. So now the present output is 1. Again here 0 and this is also 0, so 0 0 then there is no change, but k is changed here, but k is changed here means the output will change the next positive edge value. So until then it will same the remain the same output. So here k is changed, so see there is no nothing happening in the output because whenever the clock is positive edge that time only output will change. Okay, fine. So see here, 1 1 is there, so it is going to toggle the previous output. So previous output is 1, it is going to toggle the previous output, the output is equal to 0. And q bar is just an alternate of a q. If here 0 is there means here 1, here 1 means here 0. Okay, simply we are going to invert. So this is what the timing diagram of JK flip flop. Okay. Fine. And the excitation table, see, this is the characteristics table of a JK flip flop, that is 2 times 0 0 taken, 0 1 1 0 1 1. So here present state is 0 0 no change. So Qn is repeated again, 1 is repeated again. For this 0 0, here it is 0 0 only, 1 1 it is 1 1 only. But for C, these two condition, 1 1 means look at the present state, it is 0, so it is going to toggle the present state, so this 0 is changed into 1, and here 1 1 present state is 1, it is going to toggle the present state, so the value is equal to 0. Okay, so now I'm going to construct the excitation table. So Qn and Qn plus 1 is going to act as the input. So have a look at this, 0 0 here is there here. So the corresponding input combinations are first and third, that is 0 0 0 1. So j is 0 and k is don't care. See, then what 0 1 condition, 0 1 here one is there and here one is there, that is this one and this one. So 1 1 0 1, so it is 1 don't care. Fine. And 1 0, here 1 1 0 is there and here 1 1 0 is there. So 0 1 1 1, so don't care 1. Very good. Then 1 1, here 1 1 1 is there and here 1 1 1 is there. The corresponding values are 0 0 and 1 0. That is 0 0 1 0, which means this is don't care and this is 0. So don't care 0. Okay. So this is what the excitation table of JK. Then the characteristic equation. So characteristic equation means we are going to find the expression for q of n plus 1. Look at the how many places q of n plus 1 value is equal to 1. So 1, 1, 1. So totally 4 places the values are 1. So 4 places are marked and the pairs are identified and the expression is j q bar plus k bar q. So this is what the characteristic equation of JK flip flop. Okay. So now in this JK flip flop there will be a drawback is there. That drawback is called as the lazy. Okay. So we have checked 0 0 0 1 1 0 1 1 4 conditions in JK flip flop. Okay. So while checking these 4 conditions, any one of the conditions will not provide the output correctly. So we are going for one more feedback in any one of the input condition. Okay, see, as you already know, J and K clock are equal to 1, toggling takes place. Here the propagation delay has also been reduced, so the output will be given out at the instant input is given. So there is a toggling again, that is, we are going for one more iteration for any one of the input condition, that is this 1 1 condition. Okay, so this condition is called as race around condition. So what is our ultimate aim? When the clock is one, see the clock is this is one clock time period. Okay, up to this one clock time period. So within this one clock time period, we are supposed to get one output. If suppose within this time period we are getting like this two output means then that case is called as race cases. So for each clock, only one output. Have a look at this diagram. This is clock signal, and this is J and K input. And have a look at this. Here J is one and K is one. And look at the output. Here the outputs are changing two times. Similarly, for this J is one, K is one, and the clock is one. Outputs are changing two times, but these two are not a valid outputs because for each clock pulse only one output, but here see one time one is there, then zero is there, then one is there, three times outputs are changing. So this problem is called as race problem. Okay, race problem or race alarm condition. So how to overcome this race alarm condition? Which there are three methods here. The first one is increasing the delay of flip-flops. That is some of the gates we have used for designing in a flip-flop. So each and every flip-flops gates are having some delay. Okay, so we supposed to increase that delay to overcome this race condition. This is one method, and another method is definitely we supposed to use edge triggered flip-flop. That is, if you are using level triggering, definitely raise RAC problem will comes. So to avoid the RAC problem, do not use level triggering. You should go for edge triggering. And third one is uses of Masterslave JK flip-flop. So Masterslave JK flip-flop is one of the method, one of the design to solve the RAC problem. Okay, let me explain what is Masterslave in the next slide. Right? Fine. So Masterslave JK flip-flop. The Masterslave flip-flop is basically a combination of two JK flip-flop. Yes. So one JK flip-flop is going to act as a master, and another one is going to act as a slave. Okay, right. So in addition to these two flip-flops, the circuit also includes an inverter. Because two flip-flops, so we need to use two clock pulses. For each, this is one flip-flop and this is one flip-flop. And here I am going to give you the clock pulse. Okay. If I am giving the same clock pulse to both the devices, then both the flip-flops will work simultaneously. So for that purpose only, here I am going to use one inverter. Okay, so if a clock is 1 means this will work and this won't work because here inverter is there, so this value is 0, so it won't work. If clock is 0, this won't work and this will work. So for that purpose only here I am using inverter. Fine. So inverter is connected at the clock pulse only. Okay, see, clock pulse is 0, master flip flop, then CP1 slave flip flop, quite then opposite each other. See here the logical diagram of Masterslave. This is one JK flip flop and this is another one JK flip flop. And here set and reset, that is a JK input is given. The same JK input is the second flip flop for JK inputs are connected from the previous flip flop for Q and Q bar. And the inverter thing is clock. This is clock and here one inverter is there. This inverter output is connected to the slave. Okay, so definitely for each clock pulse, see, this is the one of the clock pulse. Here the value is 1 and here the value is 0. So now I'm going to apply this clock pulse here. So value is 1 and this is positive edge triggering. See, there is no bubbles here. So when the clock pulse is 1, master will work. So master will produce some output. Okay, when the clock is going to 0, so now this slave will work. So the previously stored output of this Q and Q bar now will comes as an input here. Now the slave will work. So JK is 0, 1, so the output is 0. So we are getting only one output. Hence, the race or condition problem was solved. Okay, so this is the way to avoid the race around condition. Okay, so two JK flip-flops are needed and one inverter is needed. Definitely we need to connect this inverter at the clock pulse. Okay, because we are having two transition in the clock pulse. So when it is 1, master will work. When it is 0, the slave will work. And this is the time diagram of master and the slave. Okay, see, for the entire clock pulse, first this is positive So master will work, and when the negative started from this point onwards, at this point negative, so at that time slave will work. So only one output only pending. This is what the master slave flip flop. Okay, right. And this is a working condition of a master slave. The next thing is a D flip flop. Fine. So D data or delay flip flop. So it operates only positive clock transition or negative clock transition, similar to the SR and JK. Whereas our T latch operates with the enable signal. Yes, latch will operate with enable signal, but flip flop will operate with a clock signal. Okay. Fine. And we have a look at this. This is in a symbol of a D flip flop. So here only one inputs D and clock pulse. Then here clear signal, and here a preset signal outputs and inverter output. These are all the important mandatory inputs and outputs for any kind of flip flops. Okay. And see, we can derive this D flip flop from SR, and we are going to connect one inverter between S and R. Okay, this is S and this is OR in SR flip flop. So we need to connect one inverter here. So which means, see, when I'm going to give a D value is equal to 0, what will happen? This is 0 and R will 1. According to the SR flip flop, 0, 1, what will be the output? Q output is equal to 0 and Q bar is 1. Okay, and when I'm going to change D value is equal to 1, here S value is 1, but 1, so here the output is 0. So 1, 0 according to the SR flip flop, this is 1, 0. So which means when D is equal to 0, Q is equal to 0. When D is equal to 1, Q is equal to 1. This is the concept of D flip flop. That is a data flip flop or delay flip flop. Data, whatever input you are giving in the place of D, the same will goes to the output. Okay, here there is no the conditions like SR and JK. Okay, only two conditions are allowed. 0, Q is 0, D is 1, Q is 1. Have a look at this. D0, don't bother about these things. Okay, D0, Q is 0, D is 1, Q is 1, D0, Q is 0, D1, Q is 1. That's it. Okay, and this is a diamond diagram, so we can easily draw the diamond diagram for this cube. So have a look at this. It will work only when the clock is high. So see here the clock is high, so the time this time only it will work. See this time D value is equal to 0, so Q is equal to 0. Okay, next when clock is high, so here clock is high, at this time D is equal to 1, so here Q is 1. Next here, the first half of this Q is equal to 1. Okay, so for this output is equal to 1, and this clock Q is equal to 0, so here output is equal to 0. Similarly for here Q is D1, Q1, and here also first half it is 0, second half it is 1, so 0 it is 1. Okay, next characteristic equation and excitation table. So characteristic equation we can easily find. See, uh, two places the values are 1 1, so those combinations are 0 1 as well as 1 1. So see, 0 1 is marked here and 1 1 is marked here, then this is one pair, so the result is it is D, so Q is equal to D. As we know that D is equal to 0 means Q is equal to 0, D is equal to 1 means Q is equal to 1. So the characteristic equation of D flip flop is Q is equal to D. And the excitation table, quite rearrange this table. Okay, so nothing will be there, just rearrange the table, we can be able to get the characteristic equations and excitation table of D flip flop. Then toggle flip flop. So it is simplified version of JK flip flop, that is T is derived from RS and T is derived from JK. This is simple concept. Okay, fine. See the toggle input, clock, Q and Q bar, and have a look at this. This is a JK flip flop for, and here I have simply short circuited J and K with one line. So now this is P. That is, if I am giving 0, this J value is 0 and K value is 0. So 0 0 according to the JK flip flop, there is no change. If I am giving 1, J is 1, K is 1, it is going to toggle the previous output. So here previous output is 0, now this is 1 and this is 0. Okay, so this is what the working condition of toggle flip-flop. So when it is 0, then there is no change. When it is 1, it will toggle the previous output. Okay, fine. Have a look at this. 0, no risk, no change. 1, it will toggle the previous output. That is, see, the previous output is qn is equal to 0. So now it is toggled into 1 now. And 0, there is no change. So q1 directly will comes to here 1. And 1, it will toggle the qn value, then that is equal to 0. Let's find the expression for this qn plus 1. So, see, we are getting t xr of q. Okay, this is what the characteristic expression for T flip flop, and this is the characteristic excitation table. Just rearrange Q here will come and T will come here, so we can get this excitation table. Okay, and these are all some of the applications of flip flops where we can use this flip flop means we can use the flip flops in counters to count the numbers and the registers to shift the data between the devices and frequency divider circuits and data transfer circuits. And these are all the characteristic equation to table excitation table of all the four flip flops whatever we have discussed before here. Okay, and these are the excitation table of all the four flip flops. Okay, fine. Let me conclude quickly what we have discussed in this lecture. We have discussed the differentiation between latches and flip flops and the four different types of flip flops we have designed, and we have constructed a truth table, characteristics table, and has equation, excitation table, and timing diagram of all the four flip flops. And we found some drawbacks in JK flip flop, that is a race around condition. So to solve the race around condition, three methods are possible. One of the methods we have designed here, Masterslave JK flip flop. Okay, so thank you all. See you in the next lecture.